Hello and welcome to another episode of EnVisioneering Exchange, the podcast where industry leaders discuss the most important topics in sustainability, climate change, buildings, and urban efficiency. I'm Vic Marinich, Global Marketing Director for Danfoss, and I'm delighted to be the host of this podcast. You can subscribe to our show on Apple Podcasts, Spotify, SoundCloud, or wherever you get your podcasts. Today, we have Jakob Carnemark from Endeavour on the show to talk about the importance of creating sustainable data centers and specifically water use efficiency in data centers. Jakob is the founder of Endeavour, which develops sustainable infrastructure solutions. Jakob, thanks for taking the time to join the show. And can you maybe give our listeners a little more background on yourself?
Greatly appreciate the opportunity to speak with you today. My background is one of really data centers from the inception of my career. I came out of engineering school and early on started working for large enterprises in telecommunication space, companies like IBM, managing their data center infrastructure. Then I went on to found a data center REIT and am working on a global data center platform now.
You've been living and breathing data centers for some time now, huh?
Yeah, absolutely.
So today we want to talk about how to make data centers more sustainable, right, in light of their increasing power, cooling, and water demands. Maybe, Jakob, can you first describe what you mean when we say sustainable data center?
Yeah, absolutely. Back in the day, when data centers were earlier in their evolution, water was not a major issue. Most data centers were in areas of municipal water. But when you get into 100 megawatt data centers, as is pretty typical today from a lot of the large hyperscalers, water use for evaporative cooling, different methods in which it's used, but most data centers still use water out there. And it can be much as, 1.5 liters per kilowatt hour of data center operation. To give you what that means in kind of millions of gallons. A typical 10 megawatt data center can use, upwards of 30 million gallons a year. And when you start to look at the landscape of data centers, where a data center is going, they're going into a lot of areas in the U.S. that are not on municipal water supplies, that are on aquifers. And so it's a lot of places in the U.S. now that are dry climates, especially if you look at west of the Colorado River, pretty extremed out areas. So it's a major issue. And then if you look at globally where data centers are going, as populations increase in hot, flat, and crowded parts of the world, using potable water for data centers is not only not sustainable, it's just not a good thing to do from a standpoint of. So it's an area that we've been really focusing on is what is the underlying technology that we can develop to make data centers more sustainable, eliminate water use. So we developed an efficient way to eliminate water use in data centers. And that's what we mean by sustainable.
We've talked about data centers and chillers and other things on this podcast in the past. I think it's the first time somebody's really bringing up water as such a critical issue, but you're absolutely right. It's becoming more and more important as we see more impacts from climate change that we're also addressing water issues. So super interesting to jump on this topic here today. What do you see as some of the current challenges to creating these sustainable data centers, particularly when we start looking at energy consumption, carbon emissions, water, to your point, right? Are there different solutions depending on the size or location of the data center?
Yeah, absolutely. A couple things just to kind of stack up on that issue is, number one, you saw a trend maybe 10 years ago where a lot of folks were looking at, let's put data centers in places like Iceland or Northern Europe, colder climates, which is definitely a good thing to do. But as data centers increase, get more distributed, which is definitely the trend today, you're ending up in much, much hotter climates. So just one of the first issues in creating sustainable data center, which means not only sustainable for the earth, but sustainable for the end user, which means it has to be reliable, is as we increase temperatures, having very, very high, ambient temperatures, a lot of traditional chiller infrastructure or methods of cooling data centers just don't work at those high temperatures. And so you get into failure modes. So that's one thing that we spend a lot of time looking at. The current data center platform that we're working on, we're targeting, the ability to work in, 135-degree ambient temperatures. Another big issue in data centers today is rack density. So one of the critical things with data centers today is rack densities are increasing. There was a period there where kind of most people felt like 20, 25 kW per rack was kind of going to stabilize out. And then, of course, we had this large move to GPUs, which is happening now. So you're seeing rack densities pretty quickly of 50 kW per cabinet. So that's another issue that's coming, which is how do we build data centers that are future-proof and that can handle these much, much higher rack densities, which is another issue. It drives, when you look at moving air in data centers versus other modalities of cooling that are coming up, liquid cooling and whatnot, it's another major issue that's coming up. So we at Endeavour really focus on trying to take a more holistic view of what is happening on the IT rack side, as well as how can we look at the solution and optimize. So we focus on developing in our ThermalWorks group, the complete system, so we're able to optimize for each part of it.
Super interesting. Up to 135 ambient. I wasn't aware we were already talking those kinds of temperatures.
In some parts of the world, we are. And, when you're putting in 20-year infrastructure, you want to make sure that you're thinking about where we could be in 20 years, right?
Yeah, absolutely.
Unfortunately, we hope it doesn't happen, but in, a lot of hot places of the world, Phoenix to Mumbai to Riyadh, those temperatures are a thing.
Right. Yeah. Yeah, absolutely. The current state of the art technologies that we're talking about when cooling data centers anyway, right? I mean, we've got traditional air cooled, water cooled, and we see submersion cooling. There's talks there. Can you talk a bit about those current methods, how they differ from each other and the challenges that they have today in hitting the requirements, like you said, looking 20 years out?
I would probably kind of put them in three buckets. The original style of cooling, which was traditional chillers and chiller plants with cooling towers, are definitely not used other than in some of the hottest climates out there, just from a CapEx cost and efficiency perspective. A lot of folks have been optimizing on that and doing a lot of good work with, trim chiller plants and things like that, where they have a good free cooling mode with a chiller plant. And so you've seen efficiency increases with what you would call your traditional kind of cooling tower approaches. The other approach, which was in widespread use and is still today in data centers, was evaporative cooling, where you would mostly use outside air and you would inject water for those kind of higher temperatures. In that approach, you're moving a significant amount of air, so you're density limited. That approach is kind of, number one, you end up with humidity problems in a lot of areas under very high temperatures, as we are seeing increasingly. That approach becomes limited. And then the other thing is you're just limited on a rack density of how much air you can move through the data center. So we, from outset of our cooling innovation, and again, greatly appreciate the opportunity to talk with Danfoss and you here. We've been partnering with Danfoss for over 15 years, and we're one of the first to use the turbo core technology in data center cooling. And what we focused on is not bringing in outside air, but leveraging much, much higher density technologies on coils. So we've been doing work on things like microchannel coils for years and trying to stay current with kind of the state of the art in that technology. We've been doing a lot of work on approach temperatures on heat exchangers, which is critical to kind of efficiency and getting as close as you can to the higher or the tighter the approach temperatures you can keep on systems. That means that when it's 80 degree outside, you can still do a lot of free cooling. And so that's an important thing to keep in mind of. And so just getting back to kind of the third approach, which has been submersion cooling, which I would say is there's a lot of talk about it. It's not a widely used technology. My personal belief on immersion cooling is it is probably something that is going to take much more evolution on server densities and actually specially designed servers to really take advantage of immersion cooling. If you think about a 50 kW rack or GPUs today, we in the Edge platform and what we're doing in ThermalWorks can pretty easily cool a 50 kW rack with our current technology using air, and we can do it very efficiently. When you go to submersion cooling on a per volume basis, you're somewhat limited. So if you look at big vats and sitting on the floor and how much IT equipment can you actually fit into it, you have to look at the cost holistically, which is, what's my land cost, my real estate cost, all the other infrastructure costs. I do believe it will play a significant role as you increase on the chip design and you start to build specialty servers designed around leveraging that. We use things like submersion cooling in some of our power electronics where we get into very extreme temperatures and heat dissipation needs. So we are familiar with it and using it kind of in the power electronic space. But I don't think that these traditional servers are really there yet where it makes sense. So those are kind of the three buckets that we kind of look at from a cooling standpoint.
Then maybe we talk about a fourth bucket here, because your company, Endeavour, is pioneering a unique waterless cooling method for data centers. So can you talk a bit more about the method and how it works?
What we, for a long time in previous iterations of cooling technology that we've built in the past, we wanted to start with a completely kind of fresh sheet of paper and new approach. And that was that rather than trying to kind of optimize the amount of water use, we wanted to eliminate water use altogether. So that was one of the things that we wanted to do. We use what is essentially a new approach to an air-cooled chiller. So if you were to look at our system, it would look like a traditional air-cooled chiller to you, which I'm sure most of you people who follow cooling is familiar with. When you kick the tires of it, it's very different. And again, it's specialty built by us and in partnership with Danfoss. Some of the attributes of it to kind of explain how the system works is we wanted to be able to do a very, very high delta T across the chiller. So traditional chillers are designed for maybe a 15 degree delta T, 12 degree delta T. That's the difference between your supply and your return temperature on the water side. Our chiller is specifically designed to be able to do a 60 degree delta T. And the reason why we designed for such a unique and high delta T is that we saw the need for hybrid cooling in the data center where you were doing liquid cooling, and I'm not necessarily talking about submerged cooling, but liquid cooling at the rack, where you have things like cold plate technology at the rack, where you have much, much higher temperatures, but you would also still have a significant amount of, air-cooled equipment. And in order to do that efficiently, the ideal chiller would be able to maintain, 75, 80 kW aisle temperature for air, and then handle the specialty cooling needs of liquid-cooled racks. So that means your leaving temperature from the chiller is 70 degrees, maintaining that 75, 80 degree aisle, again, with a proper approach technology on coils. And then you're returning back maybe 130 degree water from the CDU. So one important attribute of the chiller is that, again, it's waterless. Second, it operates on a very, very high delta T. And then the third thing that we focused on was really all cooling equipment kind of has a sweet spot, right? There's been a lot of work on, well, how do we get optimized free cooling? The goal in free cooling is to get the temperature of when you can operate in free cooling mode as high as possible. The second thing is chillers, some operate under low lift, some operate under high lift chillers. You guys designed for both approaches. We wanted to design an air-cooled chiller that really had three optimized stages. One is at free cooling stage. The second one was what we would call a high temperature, when we can't operate under free cooling, but we're bringing back much higher temperatures. And the other one is, let's call it a mid-range low temperature. So we focused on a 3-stage system that was automatically optimized for each of those conditions. And when you approach it that way, and again, what we do is focus on every part of the chiller, from our use of microchannel coils to specially designed heat exchangers to working with you and or Danfoss and its engineers on control strategies on the turbo core. After years of expertise in doing this, we've gotten to the point where we're pretty efficient at optimizing across the spectrum from the chiller to the racks and the cooling. So, for example, a lot of people over the years have migrated to fan wall technology. We are today in that space as we've been able to actually move away from traditional fan wall design to get the cooling supply up higher in the data center so that, and we get much, much higher air velocities so we can build larger data centers, higher density data centers. And we've been very, very focused on fan controls and hot aisle containment and the control of that such that your fan speed or your fan energy is always optimized for the condition that you're in, rather than the days when you'd walk a data center and the fans are just running on full and they're operating at the same time no matter what the data center load are. So again, that was some of the things that went into the design. Where we are, just kind of to give you some data points, is a traditional, very good data center operating in, let's call it a immediate hot climate, like let's take Atlanta, right, which gets pretty hot for a lot of parts of the year. We're about a 9% cooling overhead annually in Atlanta using no water. And so that benchmarks well. That's probably what you would expect to see out of a very good adiabatic, evaporative cooling system. And so to be at that level of efficiency with no water, we feel very, very good about. The other thing that we focused on in that system is your data center CapEx is driven by your peak, your hottest day of the year. All data centers are designed for what happens when the power goes out, when the hottest day of the summer. And so peak PUEs really drive your CapEx. They drive your switchgear, they drive your generators. And so we spent a lot of time and probably as much energy in figuring out how could we get to the lowest peak. So our peak PUE at design conditions in a place like Phoenix are in the 1.2 range, whereas a traditional systems in a place like Phoenix would probably be 1.5, 1.6. And that's a significant amount of CapEx that's saved. So those are things that went into the design of new system. It is a patent pending new cycle that we've kind of come up with around optimizing for those attributes that I discussed. And we found ourselves kind of thinking that we were in kind of a 5-year horizon of where we thought the puck was going. What's happened in the data center space with GPUs lately and the kind of pretty regular need to cool 50 kW racks, we find ourselves, fortunately, we guessed right there of where things were going, and we find ourselves in a good spot with that technology.
20% reduction in the PUE, that's a huge burden of CapEx off the data center. So, super interesting. So you said from the outside, it looks like air-cooled chiller, but once you take a few steps closer, it's something quite unique. When you were creating this waterless cooling system, were there other technologies that were needed to support the operation? You mentioned microchannel heat exchangers. You mentioned the turbo core compressor. I mean, what technologies kind of enabled you here?
And it's important to note, while I have the opportunity to kind of talk with you about it, we have an absolutely astounding team that has worked together for years on cooling innovations. And as I mentioned, we've been strategically working with Danfoss and greatly appreciate that, as well as some other notable companies. And a lot of our success has been around maintaining those long-term development relationships. We're now looking at the next Danfoss technology coming down the pike, right? We're an early and avid tester of new things. While we don't put it out on a data center till it's ready for prime time, we're constantly kind of looking at where we believe things are going. Some of the other things that the team has been working on is we're spending a lot of time on different strategies on flows and fluids. So there, as you know, there's a lot of work being done on lower GWP refrigerants. We have adopted, a zero GWP refrigerant, and we're also doing a lot of work on hybrid fluids and nanomaterials in that space to look at continuing to improve things like approach temperatures. In the microchannel coil area, we're doing a lot of work and testing in that, the state of the art. And so those are some of the areas that we continue to kind of work and innovate on. But I will tell you that it's really been the efforts of really astounding group of PhDs that we have in the ThermalWorks group, along with really practical folks that have grown up tweaking chiller plants over many, many years. And when you put them together and they develop a great working relationship, I've just been astounded at the developments that the team has been able to do. And then we've increasingly focused on controls as well. So there's been a lot of talk of, AI and machine learning and cooling. We have been working in that space for 10 years. And I would say the underlying technology and kind of ability to drive those algorithms now is really something that's bearing fruit. And that's another area we expect to see a lot of continued efficiency gains in.
Yeah, I mean, it's interesting because no matter how great the product, a chiller or what have you, is done, right? Once it's plugged into the system, it needs to operate within that system. So you need to understand everything else going on around there to make sure that your equipment is operating maximum. So yeah, for sure, the connectivity, the intelligence in that whole system is super critical. There's a lot of the big cloud companies, and we all know who they are, right? They've committed to achieving carbon neutrality in the coming years. How does this waterless cooling technology support their goals?
That's a great question. So one of at the overall that we're focused on is what are the missing pieces of technology that are needed to get to 100% waterless, which we've achieved, but to carbon neutral data centers. And we've been on that as a team on that journey of efficiency for a long period of time. What's great about being in the data center industry, to your point on the hyperscalers, is that they are high-tech clients that are all pretty uniformly dedicated to driving sustainability initiatives. If you look at the work and what they're doing in water, not only for their data centers, but in water for communities. If you look at what they're doing for growth of renewables. So it's really a great thing to be in an industry where your core clients are not only big adopters of sustainable initiatives, but really driving the state of the art, because it makes you as a provider much more able to do that more fluidly. So as we look at achieving that, what we've been focused on, again, we wanted to make sure we nailed this platform with zero water. We wanted to make sure that when we do use energy, we're as efficient as possible with it. So we think we've kind of reached probably, not that we're not going to continue to improve, but we've taken that big bite out of how do you get a low PUE and no water. We definitely feel that we've gotten close to the bottom point in the curve there. And the next thing that we're focused on from a sustainability standpoint is how do we inject 100% carbon neutral baseload. So a lot of the cloud players are doing great work around renewable energy, wind and solar, but data centers still need to be 24/7. And in order to be 24/7, you need to have, baseload. Batteries are great. Obviously, we deploy battery storage. We're deploying energy storage in a lot of our data centers today, long-term energy storage. But still, you can get storms, as we all know, that last longer than your batteries are going to last. So you need that baseload green backup. So we're doing a lot of work right now in technology development in renewable fuels. We're scaling up a new turbine, which will run 100% on hydrogen as well as natural gas and traditional diesel from a backup standpoint. So those are areas, in addition to the cooling platform, that we're working on to kind of partner with our clients on their objectives and, quite frankly, our objectives of how can data centers be a catalyst for sustainable development, which is something that we're pretty passionate about. If you look at the amount of money and growth in the data center industry, the basic premise of Endeavour is that in this space, we can leverage really and build really strong technical teams that not only can work on the problems of better, more sustainable data centers, but in the larger program, how can we leverage these technologies for better cooling in other areas, for better stewardship of water in other areas, and for better grids. So that's really the longer arc of the journey that we're on Endeavour is making, again, those data centers a catalyst for that technology development.
A few topics there. So we talk energy efficiency, we talk no water, and we're talking carbon neutral. And you briefly touched on, I think, another critical point in data centers, and that's about reliability, right? I mean, as you said, the data centers need to be running 24/7. How can waterless cooling help satisfy those needs as well?
It used to be when you designed a data center, your big focus was on the fiber, and then your big focus was on the power, and do I have a reliable power grid, and do I have, in some cases, do I want two utility feeds? If you think about, if you're using water to cool the data center, and especially at the densities that we're talking about, if you lose water, that can actually be more dangerous for you than losing power, because your servers could still be on and they'll actually won't just shut off, they'll melt, and you're actually creating equipment damage in that case of losing water. So water has become a critical utility for data centers. And then we've already kind of touched on the water scarcity issue. It's a big issue in a lot of aquifers in the US. And when you look out wider, the reliability of water, and in some areas, you're seeing towns in Arizona, you're seeing places in Europe, you're seeing places in the Middle East that literally are rightly so saying, hey, listen, data center, you can't build anymore if you're using water, and we don't even want you in the area. So when you look at reliability, eliminating water as a source of failure is a huge part of reliability. When we dive into kind of the chiller specifically, one of the things that we did with the chiller is spend a lot of effort in what traditional air-cooled chiller or product that you would get is not necessarily a data center product. While it could cool a data center, it's used everywhere. This chiller is specifically designed for data centers. So what does that mean? The pumping infrastructure is integral into the chiller. So it makes it more reliable. It makes it easier to install. It's designed to be installed on a two-end system. So we have two pumps integrated into it. So it's plug and play for a two-end piping system, which most chillers, you spend a lot of time, building that infrastructure on site. From an electrical connection standpoint, to control systems has a automatic transfer switch for two electrical feeds built in. So a lot of the things that you would normally have to do on site, manage the controls yourself, specify, this chiller is already designed with those reliability features as part of it, which is important from a standpoint of just the coordination. And also when you think about failure zones, you want matched failure zones. Failure zone means when something goes wrong, how big of a piece am I taking out? What you don't want to have is you don't want to have a pumping chamber, for example, that you might be designing for 10 megawatts pumping system, and you have a bunch of 1 megawatt chillers, and your 10 megawatt pump goes, and you've just lost 10 megawatts of cooling, right? Which is why we design the pumping into the chiller, so that if the chiller were to go down, you're just losing one small part that's manageable. You've lost a known quantity that you can plan around. That's an important feature that goes into kind of thinking about reliability and how to design a product that's specifically suited to the issues of a data center.
So maybe let's jump back. We talked a little bit about the density of the cooling racks you mentioned, right? We thought 25 kilowatts a rack was going to be kind of the magic number, and now we're seeing 50 kilowatts a rack. What are some of the barriers to being able to cool these high density racks? Where's that number going to go, and how can a waterless cooling system help address that?
We believe, and again, this is our opinion from all of the knowledge that we've learned from dealing with cooling, I would say that back in 2013, we built a rear door phase change heat exchanger that was able to do 70 kW per rack, And so it's something that now there was no 70 kW racks out there, but we wanted to see kind of how we could go. It was basically cooling load banks at the time. And we feel that benchmark today is kind of where I feel the practical limits of air-cooled racks are. So 50 kW per rack, we can do that. And it's important to note what we're talking about is a lot of people, you can cool 50 kW rack, you put it in a room, you don't put anything else around it, or you space out your racks, you can cool 50. But the real trick is, can you cool a 32 rack unit at 50 kW per rack, which is a 1.6 megawatt hot aisle, right? That's a whole different ball of wax. Most 32 rack skids today in the data center maybe are 500, kW or something like that. We can definitely do a 1.6 megawatt 32 rack hot aisle with air very efficiently and maintain those PUEs. And back to my comment on the chiller, what we thought a lot about is that what we feel is going to happen is increasingly you're going to have specialty compute loads as you get down the road of AI and what's coming out, what's on the horizon. We felt that it was important to do as good as we could on air, but then make sure that our facilities and our technology that we deploy has the ability for plug and play liquid cooling. So when you get into cold plate liquid cooling or submersion, and again, I'm not negative on submersion, I just believe that its time hasn't come. You want to see, like you do in the Mission Impossible movies, where you have the extreme temperature compute chips where you can really get the full effect of submersion cooling. But being able to plug into, in the same environment, which is the way we've designed our data centers, you can plug in a liquid cooled rack and you can get into the 120. So I believe that air cooling, the kind of, in summary, 50, 60, even 70 kW per rack, we can definitely do with air cooled, the current technology that we have, efficiently. And then when you get beyond that into kind of the extreme densities, into 100 kW per rack, you would need to move into liquid cooling.
Mm-hmm. We spent the last bit talking about some really interesting technology, some impressive numbers around the PUEs and so on. Can you maybe reference some specific data center projects you've worked on and some of the results? I hear you just wrapped up a project in Spain, and then maybe how are efforts in the U.S. going?
We are in completing 3 projects in Spain. We're starting another project in Lisbon and moving into several other locations, which I can't mention, in Europe. In the US, we're in the process of breaking ground on 9 locations. The cooling systems are deployed and up and running in Europe and will be in the US. We have been computer modeling our cooling efficiency and kind of iterating on that technology on how to model these systems such that when we predict a PUE, we're accurate. We tend to be a little bit conservative in that. And what we found in our current deployments in Spain are exceeding the performance benchmarks that we set from the modeling. So now that we have actual data coming back from Spain, for example, some of our cooling coils and things like that, we were predicting, we'd gotten, basically able to test it to 30, even 40% higher load and achieve that. So we feel like have good margins of safety in the way in which we're designing that. And on the efficiency side, we've been exceeding those numbers. So the number that I mentioned to you in Atlanta is benchmarked from actual data that we're collecting today. We're also starting a data center development in Phoenix, which again is one of those challenging markets, but feel really good about where we are, both from the standpoint of handling those really hot days that you have, and also being able to drive an average PUE that's very, very efficient.
Mm-hmm. Wow. Yeah, impressive numbers we talked about, and it seems now they're all coming to fruition. So we've got the energy efficiency, we've got the no water, the reduction in carbon. So it sounds like super exciting path, but right then everybody always wants to know, okay, so what's next, right? So what new technologies are you working on to even further improve the efficiency of the systems? Any inside secrets you want to share here today?
On the cooling side, we're working on higher transfer rates on the coil side. So there's some technologies that we're working on in nanomaterials to increase surface areas of microchannel coils so that you can get the closer the approach temperature you can get on your coils means you're pushing your ability to do free cooling, which is important. So that's an area that we're working on. And as again, I mentioned on the fluid side, I will say we feel that we're definitely at the state of the art and looking for areas to improve. We have other teams in Endeavour, and this is an area that we're probably more focused on from a standpoint of like, where can we be helpful to the industry to kind of improve efficiency? One of the areas that we're working on heavily is in the electrical side now. And how do you get better reliability, better productization, manage, supply chain lead times? If you look at traditional data centers, there's a lot of gear there, a lot of complexity, both from a standpoint of installation, lead times. But when you look out over the supply chain, UPSs, PDUs, generator, there's so many supply constraints. If you don't have them all, you have a problem. And so we've been doing a lot of product development on making those systems simpler, more reliable, more efficient, more scalable. I'm not going to get ahead of any product announcements today on this podcast, but that's an area that we're spending a lot of energy. And then, as I mentioned, we're right now looking at multiple things in how do we get to carbon neutral baseload. So looking at ways of lowering the cost of hydrogen production. And again, systems, we are scaling up a new baseload unit, which will be able to run 100% on hydrogen. But also importantly, you don't want to have, I believe in the data center space, a hydrogen only system, because if you have a lot of data centers running on hydrogen and you get a critical storm and there's a hiccup in deliveries, you have a big problem. So you want to be able to ideally be able to run on hydrogen any time you want and when it's available, but also have things like a diesel belly tank there sitting there for those emergencies that could occur. So we've been looking at sustainability through the lens of practical necessity of a data center being 24/7. And so those are areas that we're working on, and we'll have some announcements coming up here in the fall about some technologies that will be going into large scale production.
Yeah, hydrogen, we did a podcast on that a few episodes ago anyway, and it's also another one of those super interesting topics moving forward. But it's fantastic to see that you guys at Endeavour, right, have already set quite a high bar, but are looking to move that bar even higher as we move forward. So we look forward to some of those announcements. So just before we wrap up, are there any last comments you'd like to make before we end the show here today?
Just again, greatly appreciate the opportunity over almost 15 years now of working with Danfoss. They've been a great company to work with. When we first started with Danfoss, we were a very, very small company with big ideas. We're still a small company with big ideas. And it's been a great partnership. And then again, I'm really pleased to kind of talk about the work of our team, but it's really the amazing team of technologists that we have at Endeavour that are working on these great innovations. And, what our goal there is to kind of find great entrepreneurs, great inventors with a passion and a new idea and help them accelerate it to fruition so that we're only focused on infrastructure innovation, which again is a big enough palette to be focused on. But some of the team of Endeavour that are working, for example, in the water space with a lot of things to come from that. We're just very excited about what the team's doing and look forward to continuing the innovation. So greatly appreciate the opportunity to speak with you today.
Absolutely. Thanks. And of course, Danfoss, we appreciate the relationship with Endeavour as well. So that's it for this episode of EnVisioneering Exchange. I'd like to thank my guest, Jakob Carnemark of Endeavour, for joining us. Don't forget to subscribe to EnVisioneering Exchange on Apple Podcasts, Spotify, SoundCloud, or wherever you listen to podcasts. Lastly, if you enjoyed this episode, please don't forget to rate, review, and share it with your network. Thanks for listening, and talk to you next time.
This podcast is for information purposes only. The views, information, or opinions expressed during the EnVisioneering Exchange podcast series are solely those of the individuals involved and not necessarily represent those of Danfoss LLC and its employees. Danfoss LLC is not responsible and does not verify for accuracy any of the information contained in the podcast series available for listening on this site. This podcast series does not constitute professional advice or services. This podcast, including Danfoss LLC and the producers, disclaim responsibility from any possible adverse effects of information contained herein. Opinions of guests are their own, and Danfoss LLC in this podcast does not endorse or accept responsibility of statements made by guests. This podcast does not make any representations or warranties about the guest qualifications or credibility. Individuals on this podcast may have a direct or indirect financial interest in products or services referred to herein. This podcast is available for private, non-commercial use only. You may not edit, modify, or redistribute this podcast. The developers of the EnVisioneering Exchange podcast site assume no liability for any activities in connection with this podcast or for use of this podcast in connection with any other website, computer, or playing device.